Next problem on the mathematical induction for n greater than or equal to 1, that is for natural numbers n greater than or equal to 1, prove that 1 by 1 square plus 1 by 2 square plus dash 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 1 by n square is less than 2 minus 1 by n. Now we have to prove this result statement by using mathematical induction, first principle of mathematical induction. So first step is what? Denote this statement, given statement by using Pn. This is the Pn statement. And now the first step is what? We have to prove the result is true for n is equal to 1. That is, substitute n is equal to 1 in LHS and RHS. So what is LHS? If we substitute n is equal to 1, then LHS is 1 by 1 square. And RHS is what? RHS is 2 minus 1 by 1. So this is LHS and this is RHS, 2 minus 1 by 1. That is, substitute n is equal to 1. And this 1 by 1 square means is 1. And 2 minus 1 by n is what? 2 minus 1 is 1. Therefore, this 1 by 1 square is equal to 2 minus 1. And that is, we have the relation, that is the result is true for n is equal to 1. But here, what is the given n is greater than or equal to 1. So it is equal. So here is correction in the problem that prove that this is less than or equal to, not strictly less than or equal to. That is, we have equal to sign. Therefore, write here less than or equal to, or otherwise write n is greater than or equal to 2. So here is the correction in the example that write here less than or equal to. And for n is equal to 1, we have equality sign. So we have to show LHS is either less than or equal to RHS. So here we have equal to sign, means P1 is true. So correction is right here less than or equal to, here less than or equal to sign. Therefore, result P1 is true because we have here write equal to sign, here write equal to sign. So we have LHS and RHS both are same if n is equal to 1. And that is the result is true for n is equal to 1. P1 is true. P1 is true. Now, in the second step of mathematical induction, we assume that Pk is true. Pk is true. That is what? That is, substitute n is equal to k in this statement. What do we have? 1 by 1 square plus 1 by 2 square plus dash 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 1 by k square is strictly less than or equal to 2 minus 1 by k. So this is your assumption. It's called induction hypothesis. This is our assumption. And what do we have to prove? Pk plus 1 is true. So this is the second step, that assume the result is true for n is equal to k, that is Pk is true, and prove the result is true for n is equal to k plus 1, that is Pk plus 1 is true. That is what we have to show. Substitute here n is equal to k plus 1. What do we have? 1 by 1 square plus 1 by 2 square plus 1 by k plus 1 square. What is the previous term? 1 by k plus 1 square. The previous term is 1 by k square. We also write the previous term. What is the previous term of 1 by 2 square is 1 by 1 square, that is subtract 1. So k plus 1 minus 1 means k square. So this is the previous term. So substitute n is equal to k plus 1. Then 2 minus 1 by k plus 1. Now we have to show this. Means the result is true for k plus 1. Assume the result is true for n is equal to k. And show the result is true for n is equal to k plus 1. That is, we have to show this. And so for that, add 1 by k plus 1 square in both sides of this assumption, this equation, both sides of this equation. 1 by k plus 1 square, add in both sides. So what do we have? 1 by 1 square plus 1 by 2 square plus 1 by k square plus 1 by k plus 1 square is less than or equal to, right here, less than or equal to 2 minus 1 by k plus, this 2 minus 1 by k plus 1 by k plus 1 square. And then addition of these two, take as k into k plus 1 square as LCM. And so what we have? 1 into k plus 1 square. This minus, here is the effect of this minus sign on this plus sign. So minus k this into this minus k. So effect of this, right? If you write one more step here, that take this minus sign common out, that is bracket. In bracket, what do we have? 1 by k minus 1 by k plus 1 square, and then its simplification is this, that k into k plus 1 square is the LCM, and numerator is what? K plus 1 square minus k. So write first in bracket in these two quantities, that is take this minus sign common, that is we have in bracket 1 by k minus 1 by k plus 1 square, and then its subtraction is this, and then simplification of this k plus 1 square minus k is what? Its square is what? K square plus k plus 1, and minus k plus k get cancelled, so k square plus k minus 1 is the simplification, divided by k plus 1 square. Then we have 2 minus k square plus k divided by k plus 1 square, because here is the sign less than. These two steps are equal. This step and this step are equal. This step and this step are equal. But if we add 1 in numerator, then we have the larger quantity. That is less. We have the sign less than. Okay, so minus 1, delete this minus 1, that is add 1 in numerator. If you add 1 in numerator, then number becomes larger than the previous number. So here is the sign less than. Okay, and this is what? Take this k as common. So what do we have? K in bracket k plus 1. So k 1 k plus 1 cancel with this bracket, and k get cancelled. We have 1 by k plus 1. Okay, 2 minus 1 by k plus 1, and that we have to show. That is we have to show, and therefore what do we have? This is less than. Here is the sign less than or equal to. Don't write here equal to sign. What do we have to show? If we substitute n is equal to k plus 1, then we have this is LHS, and what is the RHS? 2 minus 1 by k plus 1, and the sign is what? Less than or equal. And therefore we have this is less than or equal to 2 minus 1 by k plus 1. So right here sign less than or equal to, and here is also what we have? We have this is equal to, this is less than or equal to 2 minus 1 by k plus 1, and that is pk plus 1 is true, and hence what do we have? Pk is true implies pk plus 1 is true, and therefore by first principle of mathematical induction, Pn is true for all natural numbers greater than or equal to 1. So correction is what? Here is write less than or equal to. Here write less than or equal to. Here write less than or equal to. Here write equal to sign. Here equal to. Then correction is at this place write less than or equal to. Here instead of this equal to sign, write less than or equal to, and then we have the answer of the problem. So while writing in the notebook, correction at these 2 or 3 places. Next problem, prove that 8 raised to n minus 3 raised to n is integral multiple of 5. Integral multiple of 5 means is multiple of 5. So we know that when the number is multiple of 5, if it is divisible by 5, or if we write the number in the form 5 into some integer, that is for example 5 is multiple of 5, because 5 you can write 5 as a 5 into 1. 10 is multiple of 5, integral multiple of 5. Why 10 is integral multiple of 5? Because you can write 10 as 5 into 2, 5 into some integer. Similarly 15, 20, then 25, all these numbers are integral multiples of 5, and we have to show this 8 raised to n minus 3 raised to n is integral multiple of 5 for all n greater than or equal to 1. And so we have to denote this, we have to prove the statement 8 raised to n minus 3 raised to n is integral multiple of 5 for all n greater than or equal to 1, and denote the statement by Pn. We have to prove this statement. So we denote this statement by using notation Pn. And now first step is what? We have to prove this result by example by using mathematical induction. And so first step is what? Prove the result is true for n is equal to 1. That is, show P1 is true. That is, substitute n as 1. So what do we have? 8 raised to 1 minus 3 raised to 1 is 5. and 5 is integral multiple of 5 because 5 expressed as a 5 into 1, and hence the result is true for n is equal to 1, that is p1 is true. This is the first step of mathematical induction, first principle of mathematical induction, that is prove the result is true for n is equal to 1. And the result is true for n is equal to 1, that is if we substitute n is equal to 1, we have it is integral multiple of 5. Answer is integral multiple of 5. Then in second step, what is the second step of the mathematical induction? Assume the result is true for n is equal to k and prove the result is true for n is equal to k plus 1. So what is your assumption? We assume that the result is true for n is equal to k, that is 8 raised to k minus 3 raised to k is integral multiple of 5, and that means 8 raised to k minus 3 raised to k expressed as a 5 into some integer. Take it at notation as m, because this our assumption, this is called induction hypothesis. What is your assumption? That 8 raised to k minus 3 raised to k is integral multiple of 5, means it is a multiple of 5. That is, it's expressed in the 8 raised to k minus 3 raised to k expressed in the form 5 into some integer. That is 5 into 1, 5 into 2, 5 into 3. What is the value of m? It is either 1, 2, 3, 4, 5 or any integer. Okay. So this is our assumption. It's called induction hypothesis. And what do I have to prove? That pk plus 1 is true. That is the statement. The given statement is true for n is equal to k plus 1. That is what we have to prove. That is 8 raised to, that is substitute n is equal to k in this statement. 8 raised to k plus 1 minus 3 raised to k plus 1 is integral multiple of 5. This is what I have to show in the second step. This is our assumption, and this is to prove. What do we have to prove? 8 raised to k plus 1 minus 3 raised to k plus 1 is integral multiple of 5. So what is the procedure of proof by using first principle of mathematical induction? And if we have to prove any statement by using mathematical induction, then the proof is in the two steps. What is the first step? Prove the result is true for n is equal to 1. And in second step, we assume the result is true for n is equal to k and prove the result is true for n is equal to k plus 1. That is, we have to prove this 8 raised to k plus 1 minus 3 raised to k plus 1 is integral multiple of 5. So when 8 raised to k plus 1 minus 3 raised to k plus 1 is integral multiple of 5, if it is expressed in the form 5 into some integer. So try consider this 8 raised to k plus 1 minus 3 raised to k plus 1 and try to express this in the form of 5 into some integer. So the next procedure is what? Consider this 8 raised to k plus 1 minus 3 raised to k plus 1 and try to express it in the form 5 into some integer. Then it becomes an integral multiple of 5. So this is the calculation. Now write 8 raised to k plus 1 as a 8 raised to 1 into 8 raised to k, because base is same, then addition of powers. 3 raised to k plus 1 as it is. Then in the next step again write 3 raised to k plus 1 as 3 raised to k into 3. That is 3 raised to 1. And then what do we have? 8 3 raised to k plus 5m, because 8 raised to k, what is the value of 8 raised to k from this star, from this equation, from this induction hypothesis? It is 3 raised to k. Shift this minus 3 raised to k in RHS. So what do we have? Plus 3 raised to k plus 5m. This is the value of 8 raised to k by using induction hypothesis. Obviously, in this proof, in the second step, if I have to show the result is true for k plus 1, obviously use the induction hypothesis. Otherwise, the proof is not completed. In order to prove the result is true for k plus 1, use the induction hypothesis in some step. Okay. In the previous examples, it's also happened that in the proof of second step, that is in the proof of pk plus 1 is true, you must use induction hypothesis. That is our assumption that pk is true. Okay. So here is pk is true means this is the induction hypothesis, your assumption. So use this assumption for some steps. Otherwise, the proof of the second step does not complete. So this is what 3 raised to k, value of 8 raised to k, plus 5m minus 3 raised to k into 3. This is a factorization of this 3 raised to k plus 1. Then 8, that take this 8 into 3 raised to k, and this 3 into 3 raised to k, take as 3 raised to k as common. What we have? 8 minus 3 in bracket plus 8 into 5m is 40m. Then 5 into this 8 minus 3 becomes 5 into 3 raised to k plus 40m. Take 5 as common. What we have? 3 raised to k plus 8m. And this bracket 3 raised to k plus 8m is integer, because this k is integer, m is integer, and integer power of integer is again integer. That is 3 raised to k is integer, 8m is integer, and addition of 2 integer is integer. So this 3 raised to k plus 8m is integer, and therefore what we say that 8 raised to k plus 1 minus 3 raised to k plus 1 expressed in the form 5 into some integer, means 8 raised to k plus 1 minus 3 raised to k plus 1 is integral multiple of 5, because it is expressed in the form 5 into some integer, and that is pk plus 1 is true. That is the result is true for result pn is true for n is equal to k plus 1. Hence what is the second step? That hence pk is true implies pk plus 1 is true. This is in the second step, that if pk is true, then pk plus 1 is also true, and therefore by first principle of mathematical induction we say pn is true for all natural numbers. Okay, so next problem, prove that n factorial is greater than n square for every integer n greater than or equal to 4. That is the first step is in the proof is not in substitute n is equal to 1 or p1 is true, because n is greater than or equal to 4, and that's why we prove the result is true for in first step. Result is true for n is equal to 4. This is the first principle. Either prove the result is true for in first step, prove the result is true for n is equal to 1 or n is equal to 2 or n is equal to 3 or n is equal to 4. Not necessarily pn is true for n is equal to 1. If the condition is if n is greater than or equal to 4, this is given, that is n is natural number greater than or equal to 4. So don't take n as 1 or 2 or 3, take n as 4 or 5 or 6 in first step. So denote this statement n factorial is greater than n square by using pn, and now we have to show pn is true for n is equal to 4 in first step. So substitute n is equal to 4 in LHS. What is 4 factorial? And what is the 4 factorial? Value of 4 factorial is 24. And substitute n is equal to 4 in RHS. 4 square is 16. And so 24 is greater than 16. That means 4 factorial is greater than 4 square. And hence P4 is true. That is this Pn is true for n is equal to 4. That is the result is true for n is equal to 4. This is the first step of mathematical induction, first principle of mathematical induction. That is either prove the result is true for n is equal to 1 or 2 or 3 or 4 or 5 or any natural numbers. Okay. Then in second step, assume the result pk is true. That is the result is true for n is equal to k. That is, this is our induction hypothesis. That is k factorial is greater than k square. This result Pn is true for n is equal to k, means k factorial is greater than k square. And to prove pk plus 1 is true, that is k plus 1 factorial is greater than, not equal to here. Here is write greater than sign. Here write greater than sign. Don't write equal to sign. Correction is at this place. Write greater than. What do I have to show? K plus 1 factorial is greater than k plus 1 square. That is the result is true for k plus 1. And so consider LHS and show RHS. So consider k plus 1 factorial is equal to k plus 1 into k factorial, because we know that. What is 10 factorial? 10 factorial means 10 into 9 into 8 into 7 up to multiplication up to 1. That is, if we write what is the 10 factorial? 10 into 9 into 8 into all the remaining natural numbers up to 1. That is, we can write 10 into 9 factorial. Value of 10 factorial is what? 10 into 9 factorial. While value of 100 factorial, you can write value of 100 factorial. 100 into 99 factorial, like that. K plus 1 factorial can be written in the form k plus 1 into k factorial, like 10 factorial. Or if you write 11 factorial, 11 factorial is what? 10 is 11 into 10 factorial, and is greater than k plus 1, because this k factorial, this k factorial is greater than k plus 1. K factorial is greater than k plus 1. K factorial, value of k factorial is always greater than k plus 1 for all k greater than or equal to 4. This is very obvious result, because k factorial is a multiplication of all natural numbers from 1 to k, and this is just k plus 1. So this is a very large quantity than k plus 1. So write here k plus 1 factorial as k plus 1 factorial as k plus 1, replace this k factorial as k plus 1. But what is the sign? Is greater than, because k factorial is replaced by small quantity, because k plus 1 is small than k factorial. So write here greater than sign. This side is larger than this side, and this k plus 1 and k plus 1 becomes k plus 1 square. And so what we have? K plus 1 factorial is greater than k plus 1 square, is greater than, here right, greater than, and that is the result is true for k plus 1, and hence pk is true, implies pk plus 1 is true. This is second step, and therefore by mathematical induction, Pn is true for all natural numbers greater than or equal to 4. Then we will see the definition of divisibility and the remaining problems in the next lecture.